So, welcome students. I am going to explain Franker's experiment for you all here. So, in this experiment, basically we have a filament that you can see here at this point. We are applying negative voltage to this filament. As a result, there is electric field in this region like this. Because of this electric field, electrons have a tendency to move against the direction of the electric field. So they have a tendency to move in this direction. Okay. So what will happen as we apply higher and higher electric field? At certain value of electric field, the electric field is strong enough so that the electrons in the metal overcome their work potential, work function, and start coming out of the metal. This happens so more at the tip of the filament because curvature is very high here, and because of high curvature, electric field also is very high here at this point. Okay, so more and more electrons are coming out at the tip of the of the filament. Now these electrons have come out of the filament. Now what happens? So you see that here we have a cathode here. Okay, this is cathode, K is written, right? So there is, if you see here in this particular image, the cathode is at slightly negative potential with respect to the grid. So what happens? Because of the negative potential at the cathode, the electrons that are coming out, not because of the negative potential at the cathode, also when the electrons come out of the metal, there will be some positive charge accumulated. There will be some positive charge which will be generated here. Okay, when electrons come out of the metal, positive charge will be generated here, and this will try to pull this newly formed electrons towards back into the metal, right? So we don't want that to happen. That is why we have used this grid G1 where we are applying a slight positive potential, and this positive potential attracts these electrons into the tube. Okay, so there is no accumulation of space charge. Okay, there is no accumulation of space charge near the filament. Now these electrons have entered the filament tube. Now we want these electrons to travel from the grid 1 to the grid 2 all the way up to the anode, so that they can be collected as current. The flow of electrons can be collected as current. So to achieve that, there is another grid G2 here, and if you see with respect to the cathode, this G2 has a positive potential. Okay, so this Vg2k, so this potential, if you see, this becomes what? G2, grid 2 and cathode K. So this potential is Vg2k, and this is our accelerating potential. Okay, now what will happen? Once we apply this accelerating potential, this will create electric field like this in the tube, and because of this electric field, the electrons will be accelerated towards the grid. Okay, that is why the name accelerating potential. So when the electrons are accelerated, they gather the kinetic energy, right? And in the filament there is argon gas is present. Okay, so inside the argon atoms there are electrons, and these electrons are arranged in orbits like so. You will find argon 18, atomic number is 18. So 2s2, 1s2, 2s2, 2p, 6, 3s2 and 3p, 6. 4, 6, 10, तो 12, 6, 18, yeah. So like that you will find, and then you will have next higher orbital is 4s orbital. So now in argon you have up to 3p6. So this is totally filled cell, right? So once the electrons, that is, so here there are two kinds of electrons. The electrons that are traveling in the tube, that are called, let us call them free electrons, okay, and second is electron inside the argon atom. So once the free electrons gather sufficient energy so that the electron in the 1s2, 2s2 and 3p6, so that the electron which are there in the 3p orbital, they absorb the energy of the free electrons and they are able to transition to the 4s orbital. So once the free electrons gather this much energy, that they can transfer their energy to the electron in the argon atom, so that it can jump from 3p to 4s. When this happens, the argon atom absorbs the energy of the electron, that means free electron, and the energy of the free electron drops, okay. Now energy of the free electron drops means velocity of the free electron has gone down. Now when this happens, what will happen? Okay, so we are currently at the point that velocity of the free electron has gone down. Now we will see how the velocity of the free electron is connected to the current that we are getting at the anode. So what happens? This electron will move all the way from the filament. They will pass through the cathode and reach the anode, okay. So this constant supply of electrons gives rise to a current, okay. I or I by A is equal to J. Now this J is equal to what? NeVd, where Vd is the drift velocity, okay, of electrons. So once the drift velocity goes down, the current basically goes down. So V goes down implies I goes down. Another way to look at this is like this way, that here if you see the Vg2a, the anode is at slightly negative potential with respect to the G2, okay. As a result, those electrons which have less energy, they are not able to reach the anode, okay. Only the electrons which have sufficiently high energy, that means higher than this Vg2a level, only those electrons will be able to reach anode and contribute to the current. As a result, when the energy of the electrons goes down, the current goes down, okay. So when the energy goes down, velocity goes down, and hence current goes down. So you will see initially there will be no increase in current, then there will be increase in current as you increase the potential, okay. And then what happens, that at certain point, once the electron have gathered energy equal to the excitation potential, then the electron energy will fall and then current will also fall. This will continue for some time, and then again if you go give more and more energy, then the electron energy will again start increasing and current will also start increasing. Okay, this continues for some more time till you give energy. Suppose previously when we recorded the dip that was at EP, now you gave so much potential that energy becomes 2 EP. Then what happens? Whatever electron has started from here, the electron reached half the distance needed to be traveled to reach the anode. So it has reached half of this distance, and at this time this electron has imparted its energy to the argon atom. Okay, now its energy has gone down to 0, suppose, and it again started from here because of the electric field, right? There is electric field in this region. So again this electron started getting accelerated, and before reaching the grid 2, it again gathered again the energy EP, and because of this energy it again transferred this energy to the argon atom, electron in the argon atom, and again its energy went down. As a result, when you are increasing the potential, so suppose at EP you recorded one dip and it kept on increasing afterwards, then at twice EP again you will record a dip. Okay, and this will continue for thrice EP and 4 EP, etc. Okay, so this is why you will get a graph which is shown here. So here I have reproduced the graph from your manual, and you are supposed to get a similar graph. So now I am going to explain what calculations you need to do. Okay, so what you need to do is find out from the image, okay, from the graph, you see the trend. So draw, first of all you have the data points, right? So connect all these data points with freehand. Okay, and after you have done that, from the trend of the graph find out the locations of the peak. So you have to start from the second peak, this one, and go all the way up to 2, 3, 4, 5, up to 5th peak you have to find out. Okay, so find the position of the first peak and find the position of the 5th peak. Okay, these peak positions you have to find from the trend of the graph. Suppose you have the data points like this. Okay, so suppose you have the data points like this. So there is no data point at this particular point, but this is the peak of your graph. So you have to draw the perpendicular from this point, which is supposed to be the peak of your graph, to the x-axis, and wherever that falls on the x-axis, corresponding to that whatever region, whatever value is there. Suppose there is value 30.12, whatever, I am giving some random value, then 30.12 becomes the reading, 30.12 volts. Okay, so similar thing you do for the last peak as well. So find out the reading for the V1 and 1, 2, 3, 4, 5, V5. Okay, and take V5 minus V1 and divide it by 1, 2, 3, 4. Divide it by 4. Okay, now this gives you the excitation potential of the argon electron in the argon atom. Now you have to do the same thing for the dips as well. So find out the first dip here and the 5th dip here, and take this difference. Okay, and whatever is the difference, you find out V5 minus V1 by 4, that gives you again EP. So this is from the peak and this is from the dip, and take the average excitation potential by taking the average of EP peak plus EP dip by 2. So this is how you will get the excitation potential, and once you have this excitation potential, then you also need to calculate the error in your calculation, which is delta EP. So now if you see here how to calculate this delta EP. So you have EP is equal to V5 minus V1 by, or let us call this Vn minus V1 by n minus 1. So from here if you take the log EP is equal to log Vn minus V1 plus log 1 upon n minus 1. So after that you can take differentiation on both sides. So if you want to find say df, what you do, you find df by dx and multiply it by dx. The same thing we are going to do. We will find out del f by del ep and multiply it by delta ep. So this becomes delta ep divided by 1 upon ep. That is equal to, similarly here, 1 upon Vn minus V1 and delta Vn minus V1 plus, if you take differentiation here, this will become 0 because this is a constant. So now from here you will get delta EP by EP is equal to delta Vn upon Vn minus V1 plus delta V1 upon Vn minus V1. Here we have taken plus instead of minus because this is an error, and error always add up. So now you have this delta EP calculation. Now in this formula, delta V1 is the shortest division on the x-axis. Okay, suppose from 0 to 1 there are how many lines in the graph? 10 lines, right? So 10 lines are there, and you have taken 0 to be suppose 5, and the 1 here you will have, suppose you have 0, here you have 1 on the graph, and you have taken 0 to be 5 volts and 1 to be 10 volts. In that case, your delta Vn is equal to delta V1 is equal to, how much is the difference? 5 volts divided by how many divisions are there? 10. So that is equal to 0.5 volts is your delta Vn or delta V1. Okay, so that is how you will find out delta Vn, and Vn and V1 you already have calculated this value, right, from the graph. So you have that. EP you have already calculated. So if you use this, then you will get delta EP is equal to delta Vn upon Vn minus V1 plus delta V1 upon Vn minus V1, okay, whole multiplied by EP. That is your delta EP. Now once you have obtained delta EP, in the results you will write report EP is equal to whatever value you got, those many volts, plus minus whatever delta EP value you got, that. Okay, so this is what you should report in the final one. And also you can also show the percentage error, which is delta EP by EP multiplied by 100. So I hope everything is clear. So with that, I expect you guys to come prepared from the next time when you come for the experiment. Thank you for your time. See you in the class.